All right, welcome back to our last few lessons for the electrochemistry unit, and this one is on cell stoichiometry. So as you imagine, we're going to apply stoichiometric calculations to electrochemical cells. Now, of course, as we can read right here, so in stoichiometry of electrolytic cells, the mass of element produced depends on the quantity of electricity passing through the cell. And of course, this goes back to almost a few weeks ago now when we looked at electrochemical cells. We knew that voltage of a cell depended on what materials actually made up the cell, whereas the current depended on how much of a material was there. So that was the direct link between current and kind of mass of substance being produced, or mass of substance being converted into ions. It just depends on if it's at the anode or the cathode. So we will need to work in current into our stoichiometric calculations and open up our, or a new formula. Now, just a few little things here. So kind of going back to when we first looked at cells. So charge, we know the symbol for that is Q. It's measured in coulombs. And this is the formula for charge here. Won't really need it. Same thing with current. We measure current in amperes. So a current is just the charge over time. So I want to bring this into consideration because the current is dependent really on the time here. And just notice how it's coulombs per second. So we see the term seconds in here. So a few little things that we're going to get, and this is our new equation revolving around number of moles of electrons specifically, because we're going to be dealing with half reactions. So this is our new formula right here, which we'll break it down a little later. And we have number of moles of electrons. Now, we are just identifying electrons because N is just moles, but because in half cells there's electrons showing up, and because of power sources they supply electrons, this is what we're counting, it's equal to IT over F, where I is the current, T is the time in seconds, and F is Faraday's constant, which is right here. So Faraday's constant is 9.65 times 10 to the power of 4 coulombs per mole, and time is in seconds. So the explanation of Faraday's constant, so this was kind of experimentally determined. So 1 mole of electrons carries 1.6 times 10 to the power negative 19 coulombs of charge. So that's 1 electron. So we know 1 mole is 6.02 times 10 to the power of 23. So if we multiply Avogadro's number by this, we get 1 mole of electrons carries 9.65 times 10 to the power negative 4 coulombs of charge, and that is just Faraday's constant. So just make sure time in seconds, we'll have to remember that, and current in amps. So when we get into our calculations, make a little more sense. Now, our formula here, number of moles of electrons equals IT over F. Of course, we can have different values of this equation. So this is our new equation, number of moles of electrons equal to IT over F. We can rearrange and solve for time, right? So just remember time's up here. If we need to isolate, we have to multiply both sides by F, Faraday's constant, divide by current, and we get our formula for time is equal to number of moles of electrons times Faraday's constant all over current. And if we wanted to solve for current, I is just equal to number of moles of electrons times Faraday's constant all over time. Remember, time is going to equal seconds. Current is equal to amps. Faraday's constant is coulombs per mole. Number of moles of electrons is, of course, moles. But this is going to be very important when we're solving these equations. Now, we're just kind of introducing this equation because we know normally in stoichiometry, the first step is always writing out your balanced chemical equation, which we know how to do. Second step is always find the number of moles you're given. So basically this equation right here just gives us a way of solving for number of moles. So it's just a new equation to put into our stoichiometry calculations. But before we actually get into stoichiometry, let's just do a few examples of working with that particular formula. So this right here, what is the time needed to pump 5 moles of electrons through an electrolytic cell operating at 2.5 amps? So we have a current is equal to 2.50 amps. We have is saying pump 5 moles of electrons. So I'm specifying that's number of moles of electrons. Faraday's constant is always given, which is 9.65 times 10 to the 4 coulombs per mole, and it's asking for what is the time. Well, from our equations on the previous page here, of course, having all of them memorized will help. All you really need is to remember one equation and manipulate it on your own to solve for any of the variables. But because we already solved for on the other one, we got time is equal to number of moles of electrons times Faraday's constant all over our current. Now, before I actually plug these in, just make sure that the units all match. We see number of mole of electron is in moles. Faraday's constant coulombs per mole. That's good. Current is in amps, right? So that's important. It's not milliamps or kiloamps. It's just amps. It's what we need. So therefore, we don't need to change any of our variables. So we can plug everything in as they show up. We got 5.00 moles. Faraday's constant, 9.65 times 10 to the 4 coulombs per mole. All over the current, 2.50 amps. Now when we solve, remember that, as I mentioned there before, time is going to be in seconds. So we are going to get a rather large number when we do this. So we get 193,000 seconds. Now normally this answer you could kind of leave it at that, but it does kind of help if you want to kind of take that answer and bring it into kind of a number that makes a little more sense. So that just means minutes, hours, or even days if need be. So how do we do that? Just remember conversion factors. So if we got 93,000 seconds and we want to convert it into, let's say, minutes, right? So we know if we want the unit of minute, we know every 1 minute there are 60 seconds. So when we do this conversion factor, our unit of seconds are going to cancel out. We're going to be left with minutes. So we can get a more reasonable answer, which of course is 3,216.67 minutes. Now this could be an answer as well if the question does state how, what is the time in minutes. You can easily say this, but this still isn't really like a logical answer. Like, what are 3,260 minutes? So if you want to take that and convert it once again, and maybe a more reasonable unit could be hours, you can, as long as you know the conversion factor, right? So we know in every 1 hour there is 60 minutes. So if we set up our equation like this, now we can see that minutes in the numerator, minutes in the denominator, they cancel out. The unit we're left with is hours. And of course, if we solve this equation as it shows up, we get an answer of 53.6 hours, which of course is reasonable. You can even break this down further and go into days if you want. So for example, how do we do that? We get 53.6 hours. We know that in every 1 day there's 24 hours. So of course when we do this, we get an answer 2.23 days. So basically any of these answers will be acceptable for that one right here, just because the question doesn't say what is the time in minutes, hours, seconds, or days. You can use any of these things here, but just so you make sure that you can work between all these units. So knowing how to convert from seconds to minutes, from minutes to hours, hours to days, and so on, or even going in reverse, so starting with days and then getting to seconds. So that's how you'll need to do that. So our example 2 here, we have an electrochemical cell. It causes 0.0720 moles of electrons to flow through a wire during a 3-hour period. Calculate the average current. So of course this one here, I'm just going to do it in different colors so we don't get confused. Right, so we have number of moles of electrons is equal to 0.0720. We have time is equal to 3.00 hours. Now right away this is going to be an issue. We have to convert this into seconds. So we do our conversion factors again if you want. Right, so if we have 3.00 hours and we need to get this into seconds, right, we know in every 1 hour there is 60 minutes, and to get rid of that minutes, in every 1 minute there is 60 seconds. So how this conversion factor is set up, we can tell that the units of hours cancel out, and now from our second conversion factor the minutes cancel out, and we are left with, in this case right here, 10,800 seconds. So we can take that and kind of scratch this out, and time is equal to 10,800 seconds. We know Faraday's constant is given to us 9.65 times 10 to the 4 coulombs per mole. Now for this one here, the average current. So we can use our equation from the previous page. I is equal to number of moles of electrons times Faraday's constant all over our time. So we take our 0.0720 moles, multiply by 9.65 times 10 to the 4 coulombs per mole, and divide by the time, 10,800 seconds. And we get our current, our average current, is equal to 0.643 amps. And that is the unit we use for this equation. So of course, all this is just kind of showing you how you can solve for time, you can solve for current, or even number of moles of electrons. Now for the most part, this is just going to be one of the calculations that's tossed inside of just a bigger stoichiometry problem. So for example, like, it's not too often you see ones like this. I just hold on one sec. This is what we have right here. So more specific cell reactions. We need to have the balanced chemical reaction first, and all these here, it's going to be the half reaction, generally the thing that's happening at the cathode, but we are going to deal with the half reactions of the substance reacting. And the reason the half reaction is because we need to see the number of moles of electrons. That's it. We need to see the coefficient in front of that for the mole ratio. So we're normally going to be asked for the mass produced or used, and electrode depends on the amount of moles transferred. So a separate calculation is carried out for each half reaction, and of course to calculate the mass, determine the moles of electrons using the new formula from the ratio, and we just do it in all of our normal stoichiometry steps. So we've done stoichiometry with titrations. There you go, forgot that word for a second. So now we're just going to deal with cells. So let's look at example 3 here, where we're going to apply our 4-step method for stoichiometry into one of these here. So I have example 3. It says, what mass of gold is deposited at the cathode of a gold plating electrolytic cell operating at 10 amps for 1 hour? So we'll notice our equation is already given to us right here. So if you remember the steps for all stoich problems, 1 is our balanced equation. In this case right here, it's going to be half reaction. Step 2 is always find the number of moles of our given substance. Step 3 is going to be find the number of moles of our wanted using, supposed to be the word, the mole ratio. And of course, step 4 is solve the question. So of course, in the example we have right here with the gold, step 1 is already done for us. So now we can move on to step 2, and that's find the number of moles of our given substance. So when we look at the information that's given, we're given amps and we're given hours. So in this case right here, the thing that we are actually given for from our formulas, we're actually given, we're given everything for number of moles of electrons. And our gold is our wanted, because it's asking what is the mass deposited at the cathode. So when we look at step 2, find the number of moles of our given, well, in this case right here, number of moles of electrons is equal to IT over F. So our current is 10.0 amps. Our time is 1 hour, which, remember, 1.00 hours. We do our conversion factors. So in every 1 hour there is 60 minutes. And in every 1 minute there is 60 seconds. And that gives us 36,000 seconds. All over our Faraday's constant, 9.65 times 10 to the 4 coulombs per mole. And in this case right here, we'll get the number of moles of electrons to be 0.373 0.5699 moles. Now that is of electrons. So our next step in stoichiometry is always find a number of moles of our wanted, right? So and of course we use our mole ratio. So this is where we go. Number of moles of our gold is equal to, we take the number of moles of our electrons and we multiply it by our mole ratio. Remember, mole ratio is wanted over given. Now, when we look at our wanted as gold, that's 1 over given 3. And we get 0. Case right here, 1, 2, 4, 3, 5, and so on. I just kind of ran out of room there, so I couldn't really finish that one off. So, step 1, done. Step 2, done. Step 3, now it's the last one, find the mass. So we solve the question. Now, because I just kind of ran out of room here, I'm going to go over to this one right here and finally solve. Find mass of gold. And how do we find mass? Well, mass is just equal to the number of moles times our molar mass. So our number of moles we just found our molar mass for gold, just straight from our periodic table, is 196.97 grams per mole. And we are left with mass of gold is equal to 24.5 grams are deposited at the cathode. And that is how we use our new equation to solve. So like I said, the only difference that we're kind of having right now, whereas when we done cell stoichiometry just a few weeks ago, where we did the 5-step method to predict our balanced chemical reaction, now our chemical reactions for cells is a half reaction. And then step 2 and 3, or step 2 and 4 are going to be a little different just because we have a new equation for number of moles. And it's going to be number of moles of electrons. So depending on the information that's given, you're going to have to use your new equation there at some point. So let's look at example 4. So if you think you're confident enough to go through example 4 on your own without me talking through it, just pause the video and go through it. If you just want to see me work through another one, I'm just going to go through the exact same thing, all the steps and everything like that. So for example 4, it says, how long will it take to deposit 10 grams of copper at the cathode of a copper refining electrolytic cell operating at 15 amps? So our first step is always step 1, get our balanced equation. So in this right here, it is copper getting deposited at the cathode. So we know cathode needs to be a reduction half reaction. So the reduction half reaction of copper is Cu2 plus aqueous plus 2 electrons, producing Cu solid. So this would have to be the reaction at our cathode. All right. Now, before we actually go on for step number 2 and find the number of moles are given, we can kind of highlight, what is wanted and what is given there. So right away, when we just kind of reread the question, how long it take to deposit 10 grams of copper? So right away, because we have 10 grams there, we know our copper solid is our given substance. Now, it doesn't specifically say anything about the number of moles of electrons, but because it's asking for how long will it take, we know, well, how long is just time. And our only equation that has time is number of moles of electrons times Faraday's constant all over our current. Now, current is given, Faraday's constant is a constant, so we're missing the number of moles of electrons, which is these guys right here. So that makes number of moles, not given, makes number of moles of electrons our wanted. So going back to step number 2, finding the number of moles of our given. Number of moles, because we are given a mass, number of moles is just equal to mass divided by molar mass. So we have 10.0 grams of copper. The molar mass for copper, just find it on the back of your periodic table, 63.55 grams per mole, and we get an answer of 0.157356 moles. Next step is we find the number of moles are wanted using our mole ratio. And of course, to do that, I'm just going to scroll down a little bit here. We have number of moles, in this case right here, it's the electrons we're looking for. It's going to equal to number of moles of copper times our mole ratio. So that takes what we just solved for up here, 0.157356 moles times our mole ratio. Remember, it's wanted over given, so the coefficient from our wanted is 2 over the given is 1, and that gives us 0.3147128 moles. And finally, now that we have that, our fourth step in stoichiometry, solve for time. So once again, time is just equal to number of moles of electrons times our Faraday's constant all over our current. So number of moles of electrons we just solved for. Faraday's constant is always given. And of course, current is given in the question. Just kind of scroll up here at 15 amps. And just like before, of course, we are going to get an answer in seconds. So we get 2024.65 seconds. Now, because this question does not state or to simplify it into minutes or anything like that, it's just how long it will take. So this answer will definitely be acceptable if you had it right correct number of significant digits, or you can do a conversion factor to get 33.7 minutes, which is also a good answer. So either way, if the question actually stated, what is the time in minutes, you can easily express that like that as well. So that is kind of going the other way. But the thing is, of course, making sure if you can highlight your given and your wanted and just figuring out how to put in our new equation, you'll be fine. Now, for the last one, example 4, before we get into some of the other types of calculations. This one reads, determine the minimum mass of zinc that would have to be attached to an iron fuel tank to prevent corrosion for up to 1 year, assuming that zinc produces a current of 5 milliamps. So of course, this is the minimum mass, right? So obviously zinc is going to be the wanted. And this right here, this is going to get into the next equation about cathodic protection and stuff like that. But with this right here, it's saying it's protecting iron. So technically the reaction, we have zinc solid because asking what mass of zinc. It's going to produce zinc 2 plus 2 electrons. In this case, this is our given. Or sorry, this is our wanted because it's asking determine the minimum mass of zinc. So this is our wanted. And what we have is we have current, and we know everything is going to be up to 1 year. So we have current and time. So this is our given. Now I'm going to ask you to kind of do this on your own, so pause the video, but just know, so 1 year. Right, so you'll need to do the conversion factors for that. Just get it into blank seconds. And of course this 5.00 milliamps, right? Just remember M. This stands for milli, so just think millimeter to meter, milliliter to liter. Make sure to convert this into amps before you go. So those are all the hints I'm going to give you. So pause the video, see if you can get this one on your own. If not, I'm going to put the answer up in about 3 seconds. And once you do everything, you should get your answer of 53.4 grams. Now, as I kind of alluded to, just some of the things here. So the milliamps, this is what it's converted to when it gets into amps, so 0.00500 amps. And of course, that 1 year into seconds is this, so 31,536,000,000 seconds. And of course, when you do all that, you should get your answer of 53.4 grams. Now from here, there is a few old diploma questions here as well, where it just kind of takes you through, once again, some of these here. So using electrolytic cells and using our equations right here. So for example, what we have right here, the amount of ethanol in a person's breath can be measured in electrochemical cells. So the relevant half reactions are given below. So we have a half reaction 1 and 2. And what we have for the question, if a current of 4 times 10 to the negative 3 amps, so that unit is fine, is maintained for 10 seconds, that unit is fine as well, in this electrochemical cell, then the mass of ethanol that reacted, expressed in scientific notation, is A decimal BC times 10 to the power negative D grams. So of course for this one right here, obviously we are using this half reaction right here because we have our ethanol right here and number of moles of electrons there, right? So we know that in this case right here, we are given, this is our wanted. So of course you can apply all of the steps for stoichiometry. And when you're done, this right here, so just check the PDF of the answer key and see if you do get the answer right here. And of course, if not, just email me and we can go over it together. And then of course, same thing right here. For this diploma example, it says Canadian pennies were originally 95.9% copper, but later only became 4.5% copper in the form of copper plating on steel. So the half reaction is given here. And of course, we have the time in seconds required to plate 0.106 grams of copper onto steel using a current of 15 amps is blank seconds. So just like before, in this case right here, we are given the mass of copper. And of course, because we are asked to solve for time, the number of moles of electrons is our wanted. So you can go into these here, the equations are given to you. So you're just doing steps 2 to 4 to solve. Same thing, just kind of check the PDF or the answer key to see if you get the answers for those. And of course, if you're having trouble, make sure to send me an email so we can go over these here one-on-one through Google Meet or something. And that is it for electrolytic cells. So our next lesson is going to be on science, technology, and society for electrochemical connections. And then that will be it for this unit. So I'll see you guys then.